Okay, so working through some of these old A-level questions. WJC 2016, don't really worry too much about that. There are significant differences between the old spec and the new spec, so if something doesn't look overly familiar, you might look to see whether or not I've said it's an old unit or not. But anyway, just about everything is fairly standard, including, of course, the conditions of temperature and pressure used to show in the units. Now, for gases, there is STP and SATP. STP is at a different pressure from SATP, but generally, all thermodynamic temperatures are 25 degrees Celsius. Okay. Now, pressure, of course, depends on which side of the Atlantic you're on, and also how old the tables that you're looking at are. Okay, these days in the UK and Europe we use 1 bar. The US still believes in atmospheres, and before the tables were changed in the very early 1980s, the UK was the same with atmospheres. So probably a longer answer than the WJEC would have been looking for, and they'd probably take off points, quite frankly. But anyway, there's that answer. Now, what we're doing here is we're taking 45.2 grams of phosphorus chloride, and you're told the molar mass from this, and you're asked how much heat's coming off, knowing, of course, this standard enthalpy of change of formation. Well, that minus 463 kilojoules per mole means that 1 mole has a heat change of minus 463 kilojoules. And 1 mole, of course, weighs 209 grams. So therefore, 209 grams is associated with minus 463 kilojoules. Thus, all we have to do is set up a little ratio. We know that 209 grams gives us minus 463 kilojoules. We want to know X, how much heat we're going to get from 45.2 grams. Work that through, and we get X is minus 100 kilojoules. However, we're asked for the heat evolved, and that takes care of that minus. That's what that minus sign means. The reaction is losing that 100 kilojoules. It's giving out that 100 kilojoules. 100 kilojoules is evolved. So that's the actual answer, is plus 100 kilojoules evolved from that 45.2 grams. A similar type of question in experiment enthalpy change combustion of methanol measured, found to be minus 680 kilojoules per mole. Calculate the mass of methanol for 18.7 kilojoules. So last question, you were given the mass and asked for the energy. This question, we're given the energy and asked for the mass. So anyway, methanol, for some reason, they don't give you the molar mass, or the MR this time, but it is trivial to work it out, 32 grams per mole. That tells us 1 mole minus 680 kilojoules, i.e. 32 grams is minus 680 kilojoules. Now, as far as this number goes, in the last question, we had to, at the very end, say, well, the calculation we got was minus, but then, of course, the wording allowed us to change it to positive. Same thing here in reverse. We're told the energy released was 18.7. In other words, the energy change is minus 18.7. So therefore, throw that into our little ratio. Again, 32 grams is responsible for minus 680 kilojoules. So X is responsible for minus 18.7 kilojoules, X being the mass of methanol of interest. Throw that in, and we get 0.88 grams. Various other ways to do it other than just purely setting up the ratio. You could do other ratios as well. You could have X is minus 18.7, where 32 grams is minus 680. However, as long as you have the appropriate things matching up with the ratio, it doesn't matter which way around you put it. And I always feel that spelling out a ratio at this stage of a calculation is the best way to go. Moving into the special delta H section, as I call it, and we want the standard molar enthalpy change of formation of magnesium carbonate. Now, when we do a formation, we are making the substance of interest. Thus, MgCO3 is a product, and it's going to be 1 mole of it because it's molar here. Now, later on, we won't be spelling out its molar because really that molar is redundant. The standard enthalpy change of formation defines that you are making 1 mole. Okay, now we make that 1 mole, we form that 1 mole from its elements. So the elements here, magnesium and carbon and oxygen, and of course you have to balance it, but this is fixed. So we need 3 oxygen atoms on the left hand side, which means we have to have 1.5 or 3 halves O2. Then of course it is standard, so therefore that's the standard state of magnesium, as for all metals except for mercury, is a solid. Carbon of course is a solid. You could put in graphite here if you wanted to show off, but generally saying carbon solid should be good enough, and of course O2 is a gas. Now again, we want an equation for the standard molar enthalpy change of formation of ethanol. And so again, we're making 1 mole of ethanol from its elements, carbon, H2, and O2. Again, got to balance based on there being 1 of these. So it's 5 plus 1, 6 hydrogens, so 3 H2, and 2 carbons, so 2 carbons, only 1 oxygen atom, so half an O2. And then again, put in the states, the phases. Carbon is a solid, hydrogen and oxygen are gases. Why can we not measure this enthalpy change directly? In other words, why can't we just throw 2 moles of carbon, 3 moles of hydrogen, and 1.5 moles of oxygen, a little reaction container, stew them up and make a mole of ethanol? Well, first thing is that the elements don't react, right? Graphite does not sit there and react under some standard conditions with hydrogen and oxygen. Now, if you were to force them to go, I mean, for example, you can make hydrogen and oxygen come together to make water when you put a whole lot of energy into it. Well, then you'd make some stuff, but it'd be a big, massive mixture of stuff. There's no good way to do, under most circumstances, or control complex formations like this one. Question 5, we're now moving from formation to combustion. Notice here that we don't include that word molar because it is assumed in the definition. So anyway, what's combustion? Okay, combustion is when we react with O2 to make oxides. And of course 1 mole involved in the definition. Thus the heat of combustion is when you take a substance, 1 mole of that substance, react it with O2, and the products are the oxides of the atoms within the original molecule. So now we'll talk about the combustion of methanol, right? Equation corresponding to the standard enthalpy change of combustion. So that means we take 1 mole of methanol, we react it up with O2, and we make its oxides. Oxide of carbon is CO2. Oxide of hydrogen is dihydrogen monoxide, otherwise known as H2O. Got to balance based on this being 1. So there's 1 carbon, so 1 CO2. There's 4 hydrogens, thus 2 H2O. And now we count the oxygens. We have a total of 4 on the right-hand side. 2 plus 2 is 4. We've already got 1 in the methanol. Can't do anything to change that 1 in front of the methanol, which means there has to be 3 from the O2s. So we need 1.5 or 3 halves O2 again. So now we're doing some calculation, energy cycle, to calculate the enthalpy change of formation of carbon monoxide. Well, there's carbon monoxide right there. Enthalpy change of formation is making it from its elements, which are carbon and oxygen, right there. Okay, and they're in the standard state, 1 carbon and half an O2 in the gas, because we only want 1 oxygen there in the product. So what we have to do is to get that heat of formation, which is now that top arrow, is we have to go in this direction, right, which is effectively combusting, if you like, CO2. There's an extra half O2 floating around in there somewhere that we're not going to worry about. But anyway, this takes us to CO2 and costs minus 394. And then we've got to go from here back up here. So going from CO to CO2 is minus 284. So going back up here is minus 284. Put all that in your calculators or do it on your fingers or abacus or whatever is needed, and you get minus 110 kilojoules per mole. Rather a long question that will have a short answer. The equation for the reaction that represents the enthalpy change of combustion methanol shown below. Estimate the enthalpy change of combustion of methanol by using the following table explaining how you obtained your answer. So what we see here is we see that we have 3 bigger alcohols, right? Successively 4, 5, 6 carbon atoms. Now let's look at the differences in the heat of combustion. And what we find is that when we go between butanol and pentanol, there is a difference of 653. So in other words, adding a carbon atom gave you another 653 heat of combustion. How about between pentanol and hexanol? Do the maths, and you see that again 653 difference. So the assumption we can make from this chart, and of course it's an assumption that was mentioned in the alcohol module and the combustion module, is of course that every time you add in another carbon with its associated 2 hydrogens, you get more combustion by a fairly constant number, 650 to 655, and these data here are about 653. So all we got to do is count backwards. Let's look at propanol, which has 1 fewer carbon than butanol. So we'll just take 2678 and now subtract 653 from that, and we get 2025. Go down to ethanol, take away another 653 worth, and we get 1372. So methanol, take one more set of 653 away, and we get 717. Okay, now I should notice I've been extremely cavalier with my minus signs there and so on. I'm essentially just ignoring the fact that it was a minus when I'm talking about subtracting things. What I want you just to notice that from there to there 653, from there to there 653. So we just continue to remove a little chunk of 653 from the number to get down to our estimated value for methanol. So a question, it was the last part of a bigger question, but it's very relevant here. Students then found out the enthalpy change combustion of a higher relative molar mass alcohols. They found as you got more carbon atoms, the value of the enthalpy change combustion became more negative, just like we saw in the last question. So again, we'll start off with, let's write the equation for the combustion of propanol. So we'll take 1 propanol, and remember this is fixed as 1, react it up with O2 because that's what combustion is, and then making the oxide, so carbon dioxide and dihydrogen monoxide. Balancing it, we got 3 carbons on the left, so we need 3 carbons on the right. We have 7 plus 1 or 8 hydrogens on the left, so we need 8 hydrogens or 4 H2Os on the right. Look at the oxygens now, 10 oxygens on the right, 1 already from the propanol. Cannot mess with that, so that means there are 9 from the O2. How do we split 9 by chunks of 2? We have 9 halves of them, or 4.5 of it. Okay. In terms of bond strengths, explain why enthalpies of combustion are negative. Well, let's think about what happens to those bonds, right? Any carbon-hydrogen bond gets broken, and the carbon double bonds to an oxygen, the hydrogen single bonds to an oxygen. Any carbon-carbon bonds are broken and become carbon-oxygen double bonds. The oxygen-oxygen double bonds, well, some of the oxygens go to double bond to carbons, some of the oxygens go to single bond to OHs. Now at this point one could use a qualitative thing, because essentially C double bond O and OH bonds are stronger than CHs, C double bond Os are stronger than CCs, C double bond Os are stronger than O double bond Os, and OH bonds are weaker than O double bond Os, but only a little bit. But I thought let's go exploring in the rest of the exam, and I was able to actually find values to illustrate this for those bond energies. So CH bonds become C double bond O and OH. Well, CH is 413, C double bond O is nearly twice as much, and OH is 50 kilojoules more. So in other words, these bonds are much stronger than the CH bonds. CC bonds 348 become C double bond O's, become 800, so more than double the strength there, so much stronger. And then O double bond O bonds, these are actually pretty weak in terms of double bonds, only about 500 kilojoules per mole, so they either become 700 kilojoules per mole or just a smidge less with the OH, only 32 kilojoules less. So C double bond O's are much stronger and OH bonds only a little bit weaker. So essentially, when you do a combustion, you're making stronger bonds. Okay, now delta H, which is of course what we're looking at, the enthalpy change, is the energy of the bonds broken minus the energies of those made. Breaking bonds is endothermic, needs energy. Making bonds is the opposite, exothermic, gives out energy. What we're seeing here is that the bonds that are made, this blue number, will be much bigger than the bonds broken, the green number, much stronger bonds in the products. So that means delta H will be negative because you've got a smaller number minus a bigger number. So it's exothermic. Then finally, why is the enthalpy change combustion of propanol more negative than that of ethanol? Well, as we saw in the last question, now we'll explain it. And the answer is because in propanol compared to ethanol, you've got one more carbon-carbon bond and a couple of carbon-hydrogen bonds that are all going to be converted to stronger bonds, because every single bit of combustion that you do gives you stronger bonds. The more carbon-hydrogen, the more carbon-carbon bonds you have to convert into these bonds to oxygen, the more energy you're going to get out overall. Okay, so again, you see this part 3 of a question, so I kind of had to change the wording a bit to get the context, but the literature value of the enthalpy change for the first reaction, so let's call that delta H1, is more exothermic than the literature value for the second one, call that delta H2. Why are they different? Explain in the answer. Well, let's see what the differences are. We've got CO and 2H2, CO and 2H2 at the start. We've got liquid methanol, and we got gaseous methanol. So let's see if we can't combine things a little bit, right? Let's say that instead of just going from CO and 2H2 completely to gaseous methanol, let's first of all go to liquid methanol. And of course, that is delta H1. And now to get back to the gas one, well, we're just going to turn liquid into a gas. That is the heat of vaporization. So essentially, just by thinking about Hess's law and this nice little cycle that we've pulled up, right? Delta H1 here going straight across is, delta H2 going straight across is delta H1 plus delta H vaporization. Delta H vaporization turning a liquid into a gas is always endothermic. So in other words, this is always a positive number. So it doesn't matter what delta H1 is, delta H2 is always going to be more endothermic than delta H1 because you're taking delta H1 and adding a number to it.